Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. And this is lecture 1 where we will be giving you a brief motivation for the topic which is coming up, and also the basic concepts of quantum mechanics which will be useful for you to have a hardcore understanding of the physics of the cryogenic electronics, right? As the name suggests, what we will be doing in the next 60 lectures is to give you a brief idea or to give you an idea such that you can work further ahead in the domain of very low temperature electronics, right? And though this discussion is directed towards quantum computing, but the cryogenic electronics can also be used for space applications where the temperature where you're operating the electronics is very, very small. So, we will first see in this lecture at least the basic building block of a quantum computer, and then what is the motivation for having a cryogenic electronics within the quantum computer, and therefore a very brief idea about quantum mechanics will be useful to gain a knowledge in this domain. So as such, the outline which we are referring to in this lecture series is give you a brief idea about quantum mechanics, what is the meaning of energy quanta. As an example of the concepts of quantum mechanics, we will look into two applications. One is a photoelectric effect, and then look into the wave particle duality, uncertainty principles, application of uncertainty principles, and then finally end up with de Broglie hypothesis and quantum tunneling, and give you a brief idea about the Schrodinger wave equation, which is the starting equation for quantum mechanical picture. Now, the idea here is why do we require cryogenic electronics, right? So let me give you a basic building block of a quantum computer. If you look at, there are three figures here: figure A, you have figure A here, figure B, figure C here, and then figure D, right? So at the core of any quantum computer is the qubit, which is figure C here, right? So figure C is the qubit. Qubit at this stage, assume it to be like a switch, and assume that using these qubits you will be able to have the logic being defined at this particular stage, right? So it's almost like a 0 and 1 which you see in conventional digital electronics is replaced by qubits. Now these qubits are typically kept at very, very low temperature of the order of few millikelvins to some kelvins here, right? So 0.02, we can even go up to 4 Kelvin. The qubits generally go up to that range, and the reason is that if you don't maintain such a low temperature, because of thermal fluctuations, there might be the state change of the qubit. This qubit might change its state, right? I'll give an example. Let us suppose I have an electron which is spinning in counterclockwise direction in this manner, right? Right? Now, because of thermal fluctuations, let us suppose the spinning either changes its rotational direction or there is a change in the speed of the electron. In both the cases, there will be a change in the state of the electron, which we don't want to happen ideally, because until and unless it is being either sort of manipulated by an external circuit or the user wants to manipulate it, there should not be any third way for the qubits to change its states. And therefore, the stability of the qubit, right, is an important aspect which one needs to look into. And so we are looking into the stability of qubit, and that's the reason when you look at the stability of the qubit, you actually work in the order of few millikelvins, right, to about few kelvins, around of the order of few very low order kelvins, so around 4 to 5 Kelvin you want to make it. Once you do that, your qubits remain stationary and they remain stable. So that is point number C, which is the basic building block of a quantum computer. Now, the information carried by these qubits have to be read by something in the outside. Just like when you do a practical in your BTech or in your UG program, you're doing a practical, say you want to measure a voltage or a current at a particular node of a circuitry. So what you do, you place the voltmeter there between the two nodes, and then the voltage difference is being shown in the LED outside, right? Now, similarly, in case of quantum computers, you also require an external CMOS based circuitry which should be able to read the state of the qubit And not only that, it should also be able to change the state of the qubit depending upon the user's requirement. And that's where point number B comes into picture. And that's this, and I will tell you this, the temperature range is approximately 4 to 0.01 Kelvin typically, which is kept here. So, and this is where our whole discussion for this whole lecture, we will be concentrating more on part number B for all our practical purposes. Now the obvious question, so, and let's look at part number D. This is more of the application stack here on the right hand side, and part number A is the actual physical quantum computer. So if you look, this is where your qubits are stationed, and its temperature is around 0.02 Kelvin to approximately 4 Kelvin. That's what this place is all about, your qubits. And then as you go to the top, this is where your CMOS circuitry will be kept, somewhere around 3.5 to 0.1 Kelvin, right? And then if you go further up, this is your room temperature here, which is 300 Kelvin, right? Somewhere here is the room temperature, right? So somewhere here is a room temperature here, and therefore there is a temperature gradient right from where the qubit is available till the room temperature, right from millikelvin order to 300 Kelvin. So you can see there is a huge temperature gradient which is maintained, or which happens in this cryo computer or this quantum computer which is available to us. Now let's go one by one. If you look at point number D now and correlate that with figure number A, you need to go one by one. So you see all my quantum devices, which is black colored as shown here, this is again a schematic view of it, is all stationed in this region, right? The quantum devices itself requires a very low temperature and you are doing it. Then control, readout and routing and multiplexing is all done using CMOS at cryogenics around 4 Kelvin, where you will keep it. So this green colored comes somewhere here, which is there, right? And then finally, external control signals, application domain, the algorithms which you develop, which will be driving the cryo CMOS circuitry for manipulating my qubit, is all at 300 Kelvin, right? So the external source, so the user is sitting outside this chamber A and using the techniques available to him using programming and applications and control signals, he or she is able to control the quantum devices here. In our case, we are using qubit. There are many other quantum devices available. I am assuming at this stage to be qubit, right? Now the obvious question asked is, why do you require CMOS therefore to be at such a low temperature? And the reason is very simple. Let's think in a counterintuitive manner, and let's assume that my CMOS circuitry is kept at 300 Kelvin. Then you can appreciate that the information which is carried out by the qubits will be actually destroyed to a larger extent by the large amount of thermal gradient and thermal noise which will be generated between the part A and the top part of the quantum computer. And therefore, if there is a large temperature differential, thermal noise and other sorts of mechanisms will come into picture which will destroy the actual signal whose floor value is very, very low, right? So it is something like this. If your quantum device has got signal here, and if you maintain the signal floor to be somewhere here, this is, let us suppose, your noise floor and this is your signal floor, and if they are separated by substantially large amount of distance, I can use a filter to separate it out. But if they are of the same nature and they are very close to each other, it becomes very difficult to us. And that's the reason we want to keep my CMOS circuitry, which is the readout circuitry as well as routing and multiplexing circuitry, very close to the qubit, so that the temperature gradients are very, very small. So please understand, so the takeaway from this one single slide is that our basic electronics, basic readout electronics, our basic IO electronics, our basic multiplexing electronics should be kept as close to the qubit as possible, right? And that's the reason we need to study therefore electronics at low temperature. So this is a general architecture which I am showing as far as cryogenics is concerned. So let's look at the global picture now. And so what we are doing is, we are now looking into this part, right, between the cryo and the qubit, and point number D, we are looking at control and readout versus quantum devices. So let's look at this figure here. So I have a quantum processor on the left hand side which is marked in blue, and this will have qubits available with me, and this is kept around less than 1 Kelvin approximately, and the classical controller is kept at this particular point at slightly higher temperature. What it does is gives you two signals. One is a control signal which feeds the quantum processor, and you can use this control signal for controlling the quantum processor. So the control signal which you get here is meant to actually manipulate your quantum processor. Now, once the quantum processor has been manipulated by the classical controller, the output of the quantum processor should be again read back by the classical controller. So there are two signals which is available. One is a control signal, another is a readout signal. The readout signal is primarily the output of the quantum processor, right? And that will be fed into the classical controller, which will be able to do it. So typically, these four important blocks happen to be part of any quantum computing overall figure. Now, these control signals and readout signals, they will be actually carried by wires, and these wires will be going across the region where classical controller and the quantum processor are meeting with respect to each other, and it is expected that the length of these wires are kept as small as possible so that its contribution, right, its contribution to the overall dynamics is as minimized as possible, is reduced. So if you have a very large interconnect, the RLC elements will increase and therefore the signals will be degraded too much. So we also need to understand and appreciate that these should be as close to each other as possible, and that's the reason you have control signal and readout signal. But please keep in mind again that the quantum processor is around 1 Kelvin or less than, much smaller than 1 Kelvin, whereas the classical controller is sitting around 4 Kelvin and so on and so forth. So you have a millikelvin here, and this is the millikelvin range, and this is the Kelvin range. So there is 1,000 times increase in the temperature between the quantum processor and a classical controller. Now please understand, and this is quite critical from the actual application of a quantum computing, please understand that whenever there is a electronics and there is a switching activity in electronics, you must have learned from your previous courses or from your UG or PG program that whenever there is a switching mechanism, there will be always a problem of power dissipation, right? So whenever you switch an element or whenever you switch CMOS circuitry, there will be a problem of the power dissipation. Now, please understand that you have to maintain the classical controller at 3 to 4 Kelvin order range, with ensuring that due to switching, all the readout circuitry, all the multiplexing circuitry don't have that much amount of output power, which will actually make it difficult to maintain lower orders of Kelvin temperature within the classical computer. So that's what is how you define the power budget of controller. So your controller has got a very specific power budget and you are not supposed to go beyond that. And this is one of the constraints of any cryogenic electronics, right? That if you have a very low temperature region, you can't afford to have a very, very high or a large change in the power dissipation characteristics of the controller. Okay, now I'll keep it to a very bare minimum basic and each one of them in a much more detailed manner later on. But let's look at the impact of cryogenic on semiconductors, right? The first one is pretty simple and everybody understands. There is always a decrease in the thermal activity because the temperature has gone down. So the lattice vibrations will reduce to the bare minimum. And therefore, the scattering will be reduced because when the electrons are traveling and the lattices is not moving too much around it, the probability of the electron free charge carriers colliding with the lattice is reduced, and as a result there will be always a concept of increased carrier mobility, right? And that will also resulted by the reduction in the electron scattering, electron phonon, electron scattering, right? So typically what we therefore understand that because of very low temperature, lattice vibrations will be reducing, thermal activation will reduce. Since the lattice vibration are reducing, scattering will be bare minimum, which will result in an increased value of the carrier mobility. This is the whole angle of it. The another aspect is that there is also a modification in the band gap, which means that the band gap, what is a band gap? I will tell you. Band gap changes. So what is a band gap? It is in energy scale, the difference between conduction band and the valence band. This is your band gap, BG. Now, we have already seen, and you know already from your basic semiconductor devices, that if you keep the band gap very high, it will be very difficult for you to generate free electrons. If you keep it very low, then there will be a very easy transition of electron from high energy state, which is EC, to a low energy state, which is EV. And while doing it, it will actually tend to emit energy of the order of the band gap, right? But with cryogenic, what happens when you go to very, very low temperature or on Kelvin temperature, this EC and EV does not remain in the same position as they are, right? There will be a change. We will not discuss qualitatively or quantitatively at this stage, it's too early, but there will be a change. When there is a change, if it reduces, then it's easier for electrons to jump back to valence band. Whereas if it increases, it becomes difficult for any electron to move from valence band to conduction band, and therefore the charge carriers reduce. So if the band gap increases, the charge carrier reduce, and vice versa will happen. So that is one thing which you should keep in mind at this early stage. Then there is always also a reduction of thermal noise, right? Thermal noise is basically KT, let us suppose. So when you change or lower the temperature, the thermal noise reduces drastically, right? And that comes as a help to us, because if your noise factor or a noise figure was relatively very high, then it might actually end up having overriding over the signal of the qubit itself, right? So it's something like this: if you're standing in a room, right, and you want to listen to something from outside, then you need to keep this room quiet, right? And then you can listen to outside and understand what is happening in the outside. Whereas if there is already within the room large number of people are talking and shouting, then outside noise or outside data will not be coming inside the room, or even if it is coming, you won't be able to differentiate between the external source and the internal source. So a good thing that comes into us in cryogenics for semiconductor is there is a reduced thermal noise there. What people are also looking into is that rather than just looking into the noise itself, we are looking into the fact that if using certain specific materials which is different from silicon, can we have an enhanced performance at low temperature, right? So see, the challenge which you will face as a designer or as a scientist working in cryogenics is that when you reduce a temperature to the bare minimum, the performance of the device actually tends to get changed, right? Let us assume that it is getting degraded, let us suppose, which means that I either require algorithm or material which will actually not sacrifice the performance of the device at low temperature. And that's where many new materials are coming into picture for cryogenics. But as of now, for this program, we will stick to silicon for all practical purposes. So let's look at the introduction to quantum mechanics, because that will be useful for you to understand the rest of the cryogenic part of the electronics, where we will be looking into how the device behaves at low temperature. And so typically quantum mechanics is different from classical mechanics in a sense that these are applicable to atomic and subatomic level particles, right? They are not applicable to large dimension particles such as man or stone or book. It is applied to atomic and subatomic level. For example, applied to electrons, right, applied to protons, so on and so forth. The second important part is that quantum mechanics also helps us to understand, both mathematically and to an extent physically, how the various particles, when they are very close to each other, subatomic particles, how do they interact, right? That is the major sort of difference between classical mechanics. Classical mechanics or classical physics takes care of action at a distance and so on and so forth. Whereas in case of quantum mechanics, we talk more in terms of probability of finding a particle at a particular point. And that comes from the Heisenberg's uncertainty principle, which we will study in the next slide. Which means that in classical physics or classical world, you very well know that a particular object is present at a particular point, and the probability of getting that object, if it has not moved from its initial position, is 1. Whereas in quantum mechanics, you won't be sure where the particle will be at a particular point, but you are sure that the particle will be somewhere between this one boundary to another boundary, right? So the probability theory comes into picture when we are discussing quantum mechanics. As I already told you, the key particles which is there are basically electrons, protons and photons also comes into picture, and they are actually being used to a larger extent, whose applicability in semiconductors and optoelectronics, right, in quantum computing especially, they are coming into picture. So the key concept which we will be dealing now in quantum mechanics and give you an idea is what is the meaning of energy quanta and how is it different from our classical world, we will look into the wave particle duality influences the presence or absence of a particle in a particular domain. Now, let's go to energy quanta, right? Now, if you look at the classical mechanics and if you look at the classical way of looking at it, it is always known that if you increase the intensity of the energy of the light, the energy will go on increasing. However, there was a hypothesis by Max Planck, and he suggested that the energy is emitted or absorbed in discrete packets, right? And these discrete packets are referred to as quanta. So if any particular particle has the energy involved is equals to h times nu, where h is the Planck's constant which you get, and nu happens to be the frequency of the wave function of the particle. So E is equals to h nu. So frequency of the light multiplied by h gives you the energy of the quanta. This was the Planck's hypothesis, right? And therefore the energy levels are therefore discrete in nature and not continuous, right? So this was the major influence of energy quanta, and therefore, as you can see at the bottom part of the slide, that the Planck's postulated that the energy is emitted and absorbed in discrete amounts, and this is known as quanta, which is given to as h nu, and therefore he was able to explain the concept of black body radiation, right? And the way the black body radiation behaves, he was able to explain using the quanta, right? Now, classical theory tells me that as the frequency goes on increasing, the intensity of the radiation goes on increasing as well, or diverges, right? And that's not correct as far as quantum explanation goes. So as a one of the major phenomena or experiment by which the concept of quanta came into picture was known as the photoelectric effect, because of which Einstein's contribution, he received the Nobel Prize for this photoelectric effect. Now, so the concept is something like this, that if you have a material and if you want the electrons to leave the material, then the energy of the electron has to be more than a specific value in order to leave the material, right? And if you look at the figure number A here, then there's an incident monochromatic light. Monochromatic means having a single lambda primarily meaning a single frequency, and single frequency light is falling onto a material. And the experiment which he does was he fell, and when it fell, there was an electron which was ejected from the material. Now, quite interestingly, and this is where the concept of quanta came into picture, was that the photoelectric effects predicted that there will be a critical frequency beyond which there will be a linear increase in the maximum kinetic energy with respect to frequency, and that can be seen at the right hand side figure at this particular point. So anything below nu naught let us assume is a constant value, right? Anything below nu naught, you will never have an electron being emitted from the target. Whereas classical mechanics says that as long as you go on increasing the value of nu or energy, more is the intensity of the light, more should be the electron coming out of it. But that didn't appear in the photoelectric effect. In the photoelectric effect, till a particular frequency nu naught, you didn't have any output coming up. But beyond nu naught, there was a steady increase or a linear increase in the maximum kinetic energy of the electron, and it was beyond nu naught. So what Einstein found was, or the experiment which we done, was half mv max square, or this is the kinetic energy of the particle, is equals to h nu minus h nu naught, and therefore this is h of nu minus nu naught. This was predicted. This half mvx square is nothing but the kinetic energy of the particle and kinetic energy of the electron, maximum photoelectron, and it is given as h nu minus nu naught. This h nu naught is referred to as work function of the material. Now, so which means that if the light is falling in quanta and h into nu, which is the incident light's energy, is less than the work function of the device or the material, it will be absorbed by the material, and as a result, the temperature of the material will increase, but there will be no emission of electrons. But when the h nu or the incident photon energy becomes larger than the work function of the device, the electrons will just steadily increase above the electron, and there will be some motion taking place here. So photoelectric effect and black body radiation experiments were two experiments which gave very critical sort of exposure to quantum mechanics at very early stage in the development of the physics. We will look into this wave particle duality in the next lecture. Thank you very much.